So who's your pick to win March Madness?
I have zero idea. I don't even know who's playing.
You need to like make a bracket.
I didn't even know it was happening.
Really? I mean,
I mean, you could.
no, because you're allowed you're allowed to follow as much as you want. But I wasn't sure if you just like made a bracket just to see if you made a perfect bracket, you win like $1 million. I think I could get.
Oh yeah, I did see that.
So
Like
just like-
Warren Buffett or
yeah. I mean, the odds you do it are like 1 in like 16 quintillion. 147. 100. Yeah.
I'm glad people enjoy it. I just don't.
I was thinking there's so many fun factors I want to figure out. Like if I had picked this under this factor, like for example, all the bracket images like first round.
This is very interesting. Can I start class? Happy Thursday. How's everyone doing? It's legitimately always nice seeing you. Love doing this. We have a medium-sized one today. This is not on the same scale as like introducing the sample distribution of sample slopes. But we kind of have a big one today. I'll probably say that every class, so maybe tame down your expectations. But we're actually getting into some census data today. We're going to talk about a question you might have front of mind for yourself, which is, education related to higher income? And we're actually going to get into the census data to try to answer this question directly. So I spent like last night pulling records from the Census Bureau, and we're actually going to examine this in a notebook. I've provided a data set, education data here, so you can just go ahead and download this if you want. I have a notebook we're going to work in, and then this should be the right one. And then we're going to talk about some issues that can arise when we misspecify our models. So we're going to talk about assumptions that go into building linear models, and we'll talk about what can go wrong. And then I'm going to show you what it looks like when things go wrong. We're going to do this all in census data. Before we get in, let's see. Any questions about the course? We have our next mini exam on Monday, so that'll just cover. We're back to our like weekly schedule here for mini exams. I'm going to post the rubric for the final project, so be thinking about that. You can work on your own if you like. You can work in a group of 2. I don't recommend working in groups larger than 2. It becomes difficult to sort of coordinate among your group members. So if you want to work in a group, find a friend and maybe share the workload a little bit. But I know a lot of you are going to work on your own, and that's encouraged as well. But I'll share a little bit more about the details and what you can expect. And I'm also going to post some examples from last semester of what people did. So you can see some of the projects that were done. But it's going to be really short. Like it's going to be like 2 slides and maybe 2 pages of writing, but that's about it. So really, I want you to be able to communicate very directly the types of things you're finding. And we're going to spend all of part 6 talking about how to craft a good project and how to communicate your findings. So I think that'll be a lot of fun. At least it was last semester. I've also posted homework 9. So you can find the file here and then the 2 data sets. I pushed the due date back to Tuesday. So feel free to submit on Tuesday. Just give you a week on that. I wanted to have it due on Sunday, but I didn't feel like that was fair. So Tuesday it is. All right. So any other questions? Anything else? Sorry for the delay on the homework grading. I know there's still 2 that are outstanding. Our grader, amazing grader, he got super busy and got a little behind on those things. So that's coming back to you hopefully by the end of this week. But you can always find my solutions to the homework. I often will post the solutions as a notebook, and you can just go through and take a look at like how I would write this up. Okay, so any other housekeeping things? Nice. So we have a medium-sized one today. This is not like on the level of central limit theorem, where, you know, I like spend all of my time thinking about the thing. This is on the more practical side. So to show the practicalities of some of the stuff we're going to do today, I constructed a data set that we're going to work with. So you can download EDU data, and you can work with the notebook here if you want to see it. I have it loaded in my browser, and I've put it in my week 11 folder. So what we're doing today, essentially, we're going to talk about the assumptions that make our models correctly specified. So remember, we talked about not needing to know the distribution of our sample. The random variable, we will essentially never be able to observe it. But what we can do is talk about the distribution of sample parameters. So the first one we talked about was the distribution of sample means. And then from the central limit theorem, we got this result where we could, use the t-distribution to construct p-values. We did the same thing with the distribution of sample parameters on the slope. So we were able to calculate the p-values of particular slope values. So testing whether a slope is different from 0. It's a really powerful question, general type of tool. But we were under some assumptions about the model itself. The p-values are only correct if the distribution is itself a t-distribution. And we're gonna walk through today some ways that we can actually no longer we can sort of like break the model assumptions where the p-values are no longer correct, or they don't actually capture the true probability of the event under the null hypothesis. So we're gonna talk through these things. And then I'm gonna show you some complications with introducing multiple variables in a regression model. And we're gonna do all of this under one example, which is education. So you may be wondering, is being in college for another year going to be worth it for your income later in your life? Like once you leave college? And so we're gonna just look at some census data to try to answer this question. The good news is that it does, and it's well worth it. Okay, so if it weren't, maybe I wouldn't show it to you, but it turns out it does. We have a couple of assumptions, and we're gonna talk about 3 of them more directly. But we have 4 in total. The first is linearity. So we have a linear relationship between our x and y variables. Essentially, we need that the actual equation that generates the data is itself a linear one, that it can't be curved or like warped in any way. The second is independence. So we need each observation to not depend on the previous observations. So if you think of like time series data, so you like plot out GDP against year, you'll see that there's a relationship here. So as time goes on, GDP will be very close to the GDP value of the year before. And so this is actually a violation of independence. This is, to be able to deal with time series data, we actually need something quite different, which we're going to talk about potentially in part 5. So this is a violation of independence. We need each observation to itself be independent from all of the previous observations, so no sequence in the data. And then this fancy word here, homoscedasticity. We introduced these assumptions last time, correct? Okay, so homoscedasticity, as you'll remember, is essentially equal variance across all values of x. So did I show you these pictures last time? The picture of homoscedasticity? I don't think we got there. I think we just talked about what the assumptions were. So essentially, we need that the error term doesn't have higher variance at different parts of the distribution. This is, for me as a econometrics student, always felt a little bit opaque. Like I couldn't quite see into it. So I've put some pictures together to sort of give a sort of intuitive idea of what homoscedasticity is intending. And we're going to talk about why it matters and how to fix the problem. The last one is normality. So we need that the error terms are normally distributed. This is one of the assumptions, but in practice, we actually don't need this so much. I'm going to talk about some of the intuition for why this is nice, but why we don't actually always require it, and how to check for whether we do. Okay, so nice. So the reason we need to care about this is if we build a model that doesn't actually match the data itself, we end up with p-values that are incorrect. So we're going to make conclusions that are not true. So if you're trying to, build models, the p-values is essentially how we make claims about the validity of our model. So it would mean that the predictions would be potentially unreliable. So this is one of those things where we talk about it, and I often don't see it done, checked in practice. But I'm going to give you all the tools to be able to do it. It's incredibly important to check the validity of your model, and we have really simple tools to be able to do it. So the running example for today is going to be education and income. We're going to try to ask this question. Is income higher for those who are more highly educated? So do people with with higher education have higher incomes? And the short answer here is yes. But we're going to try to quantify the relationship between an extra year of education and your income. How does income change? Or how much higher is your income if you have more education? And so you'll be able to find the data set just by downloading this EDU data. So you can click on this and download the data set and put it in your week 11 folder. And there's some stuff I did here that you don't need to really work with. This was just me sort of cleaning the data, some cleaning. But what we're going to do today basically starts right here. So we're going to start at this analysis part. So I'm going to show you a picture of the data, or just like a summary of the data. We have a sample. So this is, I believe it's a 10,000 sample, 1,000 rows. So we have a sample of 1,000 individuals from the population. And this is actually coming from a much larger sample on the order of hundreds of thousands. I got this from the American Community Survey, which is one of the things the U.S. Census Bureau runs. And then you can find census data from a website called iPooms, which is something we work with a lot in empirical economics. So you can just go here, get the U.S. Census and American Community Survey. And then you can just go through. So I actually just went through this website and downloaded census data, which is anonymized, so you don't know who you're dealing with. But we have a lot of information on individuals in the US because we take regular census. So just literally taken from this website directly. All right, and then I did a bunch of stuff to it, and then we end up with this. So we have a bunch of things here. All right, so this is going to be our data set. So this is like real world, real people doing real things and with real income and real education. These are real people. All right, which is always pretty exciting. So we're going to talk about sort of two parts of the model to try to check whether our models are specified. The first is the residuals. So just these green lines that we constructed, essentially the mismatch between our data and the model. And we can just construct these residuals directly. So we build a model, like a statistical model, and then we just get the residuals. So model.resid, and we'll just call these residuals, and then we can plot a histogram of them. These residuals are these epsilon terms. So the error in the model itself. So the mismatch between the data and the model. So if we're doing this in code, so if we, well, we'll come back to this in code in a second. We're a little bit out of sequence, I guess. But we can just get the residuals directly. We can also get the model directly. So every time we run the model, we get a linear equation, but we can make predictions for any x we like. So this model gives us an ability to make predictions for any x variable. So you can plug in a value of 200, and that will give us a prediction of, what's that, like roughly 7? And we can do that for every data point. So every one of our x values, we can just plug into the model to get a prediction. So this is one of the things we can do. And we can do it really directly. So again, it's just model.predict. So we're using the model to make a prediction about all of the values. And then we can just get a list of predictions. Okay, so, and then this is what we call the y hat. I'm not sure why this is looking funny here. That hat should be on top of the y. It is almost the end of the week, so might as well wear a hat. Okay, yeah, that joke never works. I don't know why you would wear a hat at the end of the week and not the beginning. I wear a hat almost every day. Okay, so this is the model prediction. We can get it very directly from code. One thing we might do is actually just plot out the residuals, how wrong the model is, against the model predictions. And this will give us a picture of where the model is more correct and more wrong. So I'm going to show you some pictures. We're going to do this with our example census data, building a model of education and income. But we're just going to run through quickly some synthetic pictures and talk about the assumptions. And you're going to tell me which picture better fits the assumption of our general linear model. Okay, so we have this model of assumption that this assumption of the model of linearity. So if I were to plot these two, which one fits this assumption better? The error term should be unrelated to the fitted value. Left or right? Yeah.
Well, the left one, because the residuals are like distributed.
Yeah, nice. So we really don't see a pattern in the residuals in the left one, where in the right one we do see a pattern. It looks kind of curved, like a U shape. So that violates the assumption that the error term shouldn't be related to the fitted value. We do see some extra information. If you wanted to draw a line through this, you could, and you could build a model on the residuals itself. And that's a problem. That's a violation of the linearity assumption. So to show a picture of this, I have synthetic data. So this is not the real data we're going to be working with today. But we have age and we have annual income. And we can see, generally as you get older, you tend to make more money just because you have kind of more work experience and you get promoted and all of these things. So we should see a positive relationship between age and education. If we fit a linear model to this, though, you can see the underlying relationship, because it's curved, it's not truly linear, we see that the model predicts higher incomes when you're low than what we actually see. When higher incomes when you have a low age, when you're young. So the model predicts values that are higher than what we actually see for a 20-year-old. And we see incomes in reality that are higher than the model prediction for when we're middle-aged. And then we again see model predictions that are too high for when you're older. So because there's this curvature to the truth, we get a model mismatch if we use a linear model. And what this translates to is a U-shaped or an inverted U-shape residual. So because the model is estimating incomes when you're low, we get a negative error for low age groups. So the error term is negative because the model itself is predicting a value that's too high. And then for middle age, we see an error term that's positive. So the actual data points are above the line. And so we see a positive error term for middle-aged people. And then for higher-aged people, we see again a mismatch where the data points are below the line. So essentially, what the model is doing is just sort of turning this linear relationship. It's like rotating it. And what we can see with the residual plot is the potential for a mismatch in the model. So we can see that there is a relationship in the residuals, which means we haven't correctly specified our model. Okay, any questions here? I would say if you're looking for for nonlinearities in your data, it's easier to see them when we look at the residuals than it is when we look at the data itself. I think this residual plot makes it easier to see that problem. Okay, any questions here? So the moral of the story is check your residual plots. We're going to do this together, and we're actually going to potentially fix a problem. So one way of handling this problem of nonlinearities, using the synthetic example I used before, we can actually introduce squared terms, so polynomial terms in our regression equations. You all know, using data transformations, how to construct polynomial terms. You just square the age variable. But this is still a linear relationship. Before, we were running this equation. So we had income being predicted by a vertical intercept and a beta 1 on age. So this was our original regression equation, this line. But if we introduce age squared, we can actually capture some of the curvature in the data itself. Because we have a square term, just like with an x square in algebra, you can actually curve the line itself. And this is still a linear regression because this is linear in the equation itself. So even though age squared isn't linear, we can run a linear regression on this and satisfy the assumptions of a linear model because this is linear in the betas. So each term is linear even though this is a polynomial term. Okay, any questions here? Okay, so nice. So the way we would do this, you'll remember, if we want an age squared term, we would take the data frame or the data set, get the column age, and then just square it. So this would give us age squared. So every age would just be squared, row by row. And then we could put the column or the variable age squared into our regression and then fit that. And this would give us a quadratic model. So really powerful here. We can do nonlinear things with our linear model. Okay, so maybe a little misleading to call it a general linear model. But the reason we call it that is because it's linear in the beta terms. All right, and then the interpretation here would be a little bit different. This is one of the more complicated things with interpreting polynomial equations. Beta 1 would be the effect of age when age is 0. So it's like when you go from 0 to 1, how does your income change? But then beta 2 would capture sort of the second order effect. It's like, how does the rate of change of age on income change as age increases? So the effect of age changes as age increases. And then we could test whether there was curvature by performing a t-test on the beta 2 coefficient. So everything else would look the same. Is there curvature to this relationship? Well, we can see that in the p-value for the beta 2. That's how we would perform that test. Okay, so we're going to do a different type of transformation with our data set, and it's going to be a log. So we'll talk about income, and we'll use a log transformation to talk about income. Okay, any questions here? Nice. So the third assumption is homoscedasticity, which is a word you can stumble over when you pronounce it. You'll hear me do that a couple of times today. We have homoscedasticity and we have heteroscedasticity. Homoscedasticity is just when residuals are basically spread out equally at every point on our x-axis. So what I've done here is just plotted the residuals against the fitted values for some generic regression equation. And my question to you is, which one satisfies the assumption? Yeah.
Would it be the second one because it's more like uniform as x increases, the variability increases?
Okay, so we're noticing that the variability increases when we increase our x variable. But I'm going to say that this is not homoscedasticity. What we want is actually for it to not change. So for the variability in the error terms to not be different. So this second, the first one is the homoscedasticity. The second one is heteroscedasticity, and I'm going to show you an empirical example of this a little bit later. But that's where we have changing variability in the error terms. So the variability in error is different, which hopefully intuitively, like you're thinking about the model making predictions and the error being related to the p-values. And if there's variability in the error, that would impact the p-values directly. We're not going to make those connections explicit, but that's kind of how we would think about it. Okay, any questions here? Nice. Okay, so I'm going to show you another picture here. This is, again, synthetic data. We're actually going to get to the real data in a second. But I have a picture of years of education on the horizontal and then annual wages on the vertical. And you can see, so in the synthetic data, I have a linear relationship between the two variables, but I have increasing variability. So just as like a contrived example, let's imagine, if you don't have a lot of education, it's very difficult for you to get very high-paying jobs. But then if you have a PhD, you can work a very low-paying job, potentially, but you can also work an incredibly high-paying job. So there's more variability in your annual income as you increase your education. And then so it sort of spreads out like this. So if we fit a linear model to this, you can see the increasing error, the increasing variability in the error terms as we increase education. So the mismatch gets larger as the model, as we increase education on the horizontal axis. So this is a problem in estimating p-values because the error is different and the error contributes to the p-value. It's like directly how we construct it. Okay. So this is a picture essentially of two different ways of constructing error terms. There's just a very direct way of constructing a confidence interval using like robust methods that account for this heteroscedasticity. And you can see when we construct the standard error or the confidence interval using just the standard confidence interval without adjusting for heteroscedasticity, we get a confidence interval that's smaller than if we actually allow for this heteroscedasticity. So if we construct p-values without accounting for heteroscedasticity, our p-values are going to be wrong. We're going to be too confident if we don't adjust for this problem. And it turns out there's a pretty easy way to make this adjustment in code. This is one of those places where I don't really like introducing something without telling you how it works, like without giving you some idea for like why it's working. But this is one of those places where I'm just going to show you how to fix the problem without doing a lot of justification. There's a bunch of work we have to do behind the scenes to be able to deal with this problem, and we're just going to let the computer do it, unless you're taking econometrics, in which case you may have to construct heteroscedastic, robust standard errors. But we're just going to let the computer do it. So the way you do it is when you're fitting the regression equation inside the fit operator, you're just going to put in heteroscedastic constant covariance. So you're just going to take this and put it in. I think Gemini would probably know how to do this. So you can just ask Gemini to give you robust standard errors. Okay, any questions here? It's generally a good idea to run robust standard errors. Okay, so this is how we handle heteroscedasticity. So we've handled nonlinearities by introducing potential polynomial transformations, and what we're going to do later today using log transformations. And then we fixed heteroscedasticity by introducing the covariance, the robust standard errors. And then the last assumption we need to be careful with, although a little bit less careful with, is the normality of the error terms. So what I've done here is I've constructed a distribution of error terms from the data. This is not sampling a bunch of times. This is one sample, and we're taking the residuals and just plotting a histogram of them. Which one of these do you think satisfies assumption 4? Easiest question of the day, maybe. Yeah. The one on, is it this? Yeah, so this is the correct one. It's a normal distribution. This one is a skewed distribution. So the assumption of normality is satisfied on the left. I'm both facing the opposite direction and dyslexic, so two stacked problems. So if it looks like a nice bell shape, this is what we want to see. But the thing is that you'll remember the intuition with the central limit theorem, where it didn't matter, so long as our sample size was large enough, our distribution of the sample means approached a t-distribution, or got very close to a normal distribution. The same is true here. We have this assumption of normal error terms, a normally distributed error term. But when the sample size is large enough, through the power of the central limit theorem, we actually don't necessarily need there to be a normal distribution. So in practice, we can actually circumvent this assumption so long as the sample size is large enough. Because this is showing us the distribution of the mismatch with our data, but the distribution of the average error term is going to follow the central limit theorem and give us a t distribution. And that's, it allows us to sort of get around this assumption in practice. Okay, any questions here? So you all want to see some data? Is education related to higher incomes? I hope it is, and it is. So we're gonna actually check this with the real world. Okay, so the first thing, when we perform some analysis on our data, the first thing to do is just to look at what the columns in the data set looks like. And we can see we have a bunch of interesting values here. So we have some demographics. We have an education column, which I'll talk about in a second. We have degree field. So we're actually going to talk about how we can control for different degrees. So I have the degree of the person when they went to college. So we can look at which majors have higher incomes. And then I have this column here, income total. So this is like your total taxable income. And this is in 2019. So this is right before the pandemic. And then we'll talk about, so EDU is your educational level. So 12 just represents 12 years of school. So this is like whether you graduated from high school. So 13 would be 1 year of college, and so on. So the first thing to do is just to get a picture of what the data is telling us. So here I have a histogram of education. So this is all of the different years and who is in our data set. So some people have less than a high school education. Most people in our data set have a high school education. We have 13, so that's like 1 year of college. 14 is 2 years of college, so that's like a associate's degree. 16 is a college degree, so that's 4 years of college. And then anything above that is all grouped into 17, which is more than a college degree. And turns out we have a lot of people in that group, lots of master's degrees. We can get a little more granular than this, but for data processing reasons, I'm just going to leave it with this. Okay, and then we're also going to look at the distribution of incomes. So this is our data frame, column, income total, and then we're just going to perform a histogram on this. And so you can see most people's income is on, we have this skewed left distribution, or skewed left distribution. So most people's incomes are very low, or on this histogram are on the lower end of the x-axis. Not necessarily very low, just on the lower end of this scale. And then we see sort of a sort of flattening out of this distribution. Okay, so we have a picture of education levels and incomes. We'll come back to this one a little bit later, but what I want to do is actually just plot out the relationship between education and income. So I've plotted this thing. I've added a horizontal jitter just because the horizontal axis is just made up of integer values, so the number of years in college. So I've just jittered it so we can see a little more of the distribution itself. Would you say this is, what kind of patterns do you see here? The vertical axis, maybe we should write this out. Vertical axis is education, is income, and the horizontal axis is education. Actually, let me just plot this. What pattern do you see here? This is income on the vertical axis and education on the horizontal. Remember, this is real data. This is real people. Someone describe this pattern. Yeah, Ben.
As your education increases, so does your income.
So we see, as we move further out on the horizontal axis, as education goes up, it looks like we might see a positive relationship with income. Yeah, what else do we see here? There's a bunch of parts to this. Yeah, Luke.
So the variability also increases as well.
So variability is going to go up. So you can see for less than high school education, the maximum income tends to be a lot lower. And then as we increase education, you can see this is like, so 16, and then 17 is like grad degree. You can see your education tends to have a higher maximum. So more variability as education goes up. Okay. And I mean, to me, this looks like it might be linear, but there's a lot of complexity here. So, but let's try to build a model. So the first thing we might do, our step 2, is to actually just write down the model. What we want is to be able to predict income using our educational variable. So we're just going to use edu as the x variable and then build a regression model to predict income. So we have our predictor and then our outcome variable. Okay, so then we're just going to take this and then put that model equation into our OLS with our data frame, and then we're just going to fit it. So we'll run this. Nice. So without giving you the interpretation, someone describe this to me. This is a classic question. I'm going to keep asking you this the rest of the semester. In homework, in class, and on mini exams. Someone interpret this for me. Can you read it? Maybe you can't. What is this telling us? Is this good for you? Like, are you glad you're in college when you see this? Yeah, Ben. The intercept, you mean?
Yeah, because they're both so small.
So Ben's pointing to the intercept and saying this is really close to 0. Or potentially, actually, this is negative. We have a negative value. We have e to the positive 0.5. So this is, the vertical intercept is actually very, very small, very negative, actually. So if you have zero education, according to this model, you're making negative money, which means maybe you're like not able to pay your bills. You're like going into debt if you don't have any education. That's what this model would tell us. What about, yeah?
I suppose the slope would tell us that as you increase in numbers of years of education, the amount you earn increases by that much. Like
Yeah. Yeah, nice. Remind me of your name.
Max.
Max. So what Max is saying is, as we increase education, every single year, an additional year of education gives us this much extra money in our salary. So our salary goes up by this much. Someone know what this number is? What?
Just small.
Small?
11,900.
11,900. So this is actually a pretty big number. We have very small numbers. So like if we have e, so 1 times e to the power negative 5, this would be a very small number. This would be like, so this thing is very small, and so multiplying it by 1 makes this whole thing very small. But in this case, we actually have a positive value, so it's e to the positive 5. So this, because it's e to the positive 5, it's like we have a very large positive number. But the way we interpret the scientific notation is a little different than this. This is, our scientific notation is actually, it's 10 to the positive 5. So each one of the zeros, e to the something, we have 5 zeros. So this is 1.19 times 10 to the positive 4. So here, because it's a positive 4, it's actually a very large number. When it's e to the negative some number, we have decimal places. So it's like, how many decimal places? How many tens are we dividing by? So here, this is actually a very large number. So it's, 1, 2, 3, 4. So this is our, this is how much our income goes up. Our annual income, remember, goes up by 11,000 or 12,000 every additional year of education we have. So if you work for like 30 years, that's 30 times this number for every additional year of education. So that's a crazy number. Okay. So do we trust this? Well, let's check the assumptions of our model. That's where we would turn to. So the first thing we'll do is just calculate the residuals. So I've gone through, and run this model. We have model, which is the regression model, and then we can just run the residual plot. So someone tell me here. This is a histogram of all of the residuals. Does this look normal? No, I don't think this does. It's like, there's definitely a skew to it. There aren't a lot of very negative values. It's definitely centered on 0, but is not centered. This turns out not to be a huge problem because our sample size is so large. So the length of the data frame is 1,000 observations, which means we're definitely in the land of central limit theorem kicking in. So we don't actually need the underlying distribution to be normal for our p-values to be interpretable correctly. So here we're actually fine, even though the distribution of the error terms is not normal. Okay, so the second thing we'll do is check the residual plot. So what I've done here is plotted on the horizontal axis, I've plotted the jittered prediction, and then on the vertical axis, I've plotted the residuals. So we have the residuals on the vertical axis, and then the predictions on the horizontal axis. And what we would want is we want to see homoscedasticity and linearity. So someone tell me, does this satisfy the assumptions of our model? Yeah, Max.
Definitely not, because the difference increases as the x-axis increases.
So we definitely see increased variability in incomes with higher educational levels. So this is heteroscedastic. All right, so we have a couple of things we can do here. Or not do, depending on the computer. So if you're looking at a blank screen, what do you think you should do with this problem? We see heteroscedastic errors. We see this picture. What do you think is something we could potentially do? I've given you 2 tools, and we could use either one of them. Let's say you're actually faced with this problem. What are you doing now? Corin.
Would you take out the data and apply log to it?
Okay, so what would you log?
It would be each one of the data points, and just log it, right? Or just the y.
The y variable? Okay, Max is agreeing. Why would you log the y variable? Is that an answer, Garrett? Yeah, why would we log the y?
Well, there's not as much like variance between the x, but there's a lot of y. Like when you're like the outliers of y are much higher than like those are set out much more than like the x's apart from one another.
Okay. So yeah, maybe we would log income. Any other ideas? Yeah.
Perhaps it could take like a weighted pair based on x or something.
Yeah, which is sort of what the robust standard errors are kind of doing, is like trying to deal with, it's like you want to kind of like reduce the variability for larger values by performing a type of weighting. Yeah. So what I'm going to do, when I see this problem, I think about income, and I've already asked you this on a mini exam actually, like examples of data where you would want to perform a transformation. This is one of those classic ones. Income, anything that kind of scales like this, like income, is a great example of something you perform a logarithmic transformation. So what I'm going to do is actually, I'm going to perform a regression model rerunning step 2 and 3. But instead of using income as the outcome variable, I'm going to use log income. And we can just take a look at this. So this is df.income log 10. And then we can just plot a histogram of this. And you can see this is actually a very different distribution. This looks normal, where the original distribution, the distribution of income, this does not look normal. So this is like very skewed, what we call zero inflated. There's a lot of pressure towards zero. But when we take a log of this, we get something that looks much nicer. And the interpretation here is like, because this is log 10, each one of these integer increases is a 10xing of income. So you're adding 1 0 to the end of your income every time you move up on the horizontal axis. So if you have an income of 4, that's 1/10 the income of 5. So this is a really nice transformation. This is often what we do with incomes. We almost never run regressions on incomes without taking a log of them because they look so nice once we log them. The distribution looks much more like what we would like. So when I run this model, I get education, I get a coefficient here. The intercept is positive now, where before it was very negative, as Ben pointed out. And we get a coefficient. So someone take a stab at this. Is actually a really hard thing to interpret. Someone take a stab at this. How do we interpret this regression output? Like, what are these coefficients telling us? What about the intercept term?
It's a positive relationship between income and education, since education increases, tends to increase as well.
Okay, so we definitely see a positive relationship here. We have education, we have this positive coefficient on education. We can see that it has a very small p-value, which means we're very confident that this is not 0. And we also see a positive coefficient on the intercept term. I'm just going to check the clock. People leaving, I always second guess myself. Love the flowers.
Thank you. Go buy them in the closet.
So our vertical intercept here is 3 log, like the log of income is 3.3, 3.2. So this tells us the vertical intercept in log terms is roughly a 1 with 3 zeros behind it. So it's like $1,000 is your annual income on average if you don't have any education. We don't really have a lot of people in our data set with that low education. We're really only looking at high school or above. But this gives us a positive intercept that we have to interpret through the perspective of logarithms. Someone make an attempt at interpreting the coefficient. Lucas told us what the sign is and that it's significant, but someone try to make an attempt at interpreting what that number is. This is a hard thing to do. Yeah.
So for every 1 unit increase in, I guess X would be the log for income, then the predicted Y would increase by 0.09, or I guess that'd be 0.09 dollars a log. I'm not sure exactly what it is.
Yeah, so that's right. So it's like every year of education, we see our log income go up by 0.1. If we go up by 1, we're going up. Our income is doubling. We're going up by 100%. So because this is log base 10, increasing by 1 log point increases our income by 100%. We're adding another 0 to it. So if we're increasing by 0.1, then it's roughly equivalent to 10%. So the interpretation here, I'm just going to show you what I've written. So this is, a log variable. So each x variable increase in education increases by some percentage impact on income. So here we're saying an additional year of education is associated with a 10% increase in your annual earnings, which is massive. That's like a huge impact, a huge relationship. But this isn't a causal relationship. Like people who go to college may already be sort of more likely to make more money in their life. There may be other factors going on here, but this is definitely a very strong relationship, 10% per year. Any questions here? I'm going to ask you a question in the future. Potentially, it's not in this homework, but it'll be in a future homework. How to interpret logs. We'll talk a little bit more about it, but it's such a common type of transformation that it's good to know how to interpret this on its own. This is just like a special one. So the interpretation here is every year of education is worth 10% extra income, which is amazing. All right, but not causal. It's associated with a 10% increase in income. So again, we've gone through and we've built this regression model. We've interpreted what it means, but we also have to check again the assumptions and to see if the model itself is well specified. This is a thing we have to do. So the first thing is we'll plot the residuals. And here, someone told me, is the assumption of normality satisfied here? This is a little bit better. It's not perfectly normal, but it's a little bit better than our last one. But again, because we're still in the world of large samples, the central limit theorem makes this a little bit less important to worry about. The second thing we'll do is check the residual plot. What about this one? Does this look a little better? How many of you think this looks homoscedastic? 3. How many of you think this doesn't look homoscedastic? 0. How many of you abstained? 1. And the rest of you are ghosts. All right, so yeah, this looks homoscedastic. The variability is very consistent across. So that's very nice. It also looks linear. There's no like shape to it. So that's also nice. This is what we want to see in the residual plot. This is like almost a perfect one. Okay. So this is all very nice. This is how we build regression models. This is like single variable regression models. But you may have noticed, I mentioned this already actually, education is not the only thing that's related to your income. If I, or like anyone in New York City, let's say each of us, like, you all graduate, you get a job in Pittsburgh. If you were to get the equivalent job in New York City, you would make a considerably more than you would in Pittsburgh. The difference in income for the same job between the two cities is very sizable. In large part just because you have to, it costs you more to live in New York City. So your income needs to be higher to be able to afford to live there. The company has to pay you more just to be in New York City. The industry you go into, so that's going to have an impact on your earnings, and like work experience. So lots of things have an impact on how much you make. I'm going to show you an example using synthetic data of some of the problems we can run into with interpreting the types of coefficients we just ran. So we built this model predicting income using education, but this doesn't tell the whole story, and I'm going to show you a picture of why this is true. Okay, so we have all these potential relationships with income. One way we can handle them is just by plotting each of them separately, building separate models, using regression for each one of them separately. So this is a picture. On this side, we have, I can never remember which stage right or left is which. This picture here shows a relationship between years of education and annual wage. This is a different number than what we did in with real data because this is just synthetic data. I've just made it up. But we see a positive relationship between these two things. The second picture shows us if we just built a model predicting annual wage using years of experience, we'd actually see a negative relationship here. This may not necessarily be true in the data, but we would see, at least in the synthetic data, we see a negative relationship between the two. So does this mean that experience has a negative impact on your wages? It's a real question for you. If we see this, does this tell us that work experience is negatively related to earnings? Ben.
More factors. Like I'm thinking graph can really tell us that. There'd be more factors to it.
So potentially more factors. Okay. Yeah. So I agree. How would more factors make this thing look negative? Why do we see this? Corin.
Something to do with multicollinearity. There's a certain variable that's very correlated with years of experience that is also responsible for decrease in the real wages.
Okay, so what if years of experience was related to something else that was related to wages? So what if, let's say hypothetically, that for every additional year you worked, that meant you were not in school? We know, I mean, it looks like school has a positive relationship with wages, but if you were not in school, you would, or if you were working, that meant you were not in school. At least if you're working full time, it's very difficult to be a full-time student. So if we plot just without using fancy terminology, we have a negative relationship between years of education and years of experience, just because you can't be doing both things at once. So we have a negative relationship between these two things. And we have this picture from before showing different relationships between years of experience and years of education. This picture. How do we deal with this? How do we know what's truly going on? Like, what's the true relationship between wages and years of education? Like, what's the true thing here? How do we get at it? What if we tried to compare two people with the same amount of experience and look at differences in income and differences in education? So we hold constant people with the same amount of experience, work experience. We just look at the same people, people with the same amount of work experience, and compare those people, the relationship between wages and education. This is what we call a control factor. We're going to include an additional variable in our regression model and then compare between people who have the same amount of work experience. And the way we do this is by including a third variable. So before we just had two variables, x and y, and then we drew a line through the data points. With three variables, we have income as the outcome variable. We have education as a predictor variable, and then we have a second predictor variable, which is work experience. This is three sort of dimensions of our data, where instead of plotting a line through it, we're actually plotting a plane. Try to fit the plane by moving it around so that it minimizes the sum of squared errors, just like we always have. I sort of hate this picture. I sort of love it. I think it gives like one kind of intuition, but we actually never kind of plot things like this because it's really hard to see what's going on. But this is behind the scenes what's going sort of into the model, what the model is doing. So what we're doing by including a third variable is holding everything else constant. We're holding constant the other variable and simply comparing two people who have the same level of work experience. So where before we just had this regression equation, we're predicting wage using education. With multiple variables, we're actually including a beta 2 times another x. So our x1 variable is education, and our x2 variable is work experience. And the interpretation is very similar, but with a small difference. Because we've included another variable, another control variable, we're actually holding that variable constant when we interpret beta 1. So the effect of one more year of education is now holding the other dimension constant. So we're holding constant work experience. And then we're just comparing two different people with the same work experience. And then for beta 2, this is the same sort of idea. We're looking at the effect of one more year of experience holding education constant. Okay, and we can do this just directly in Python. This is the last thing we'll do. I just want to run this regression, and then we'll pick this up after the mini exam on Tuesday. So we don't have work experience in our data set, but we do have age. And here's a picture showing the relationship between age and education. So age on the vertical axis and education on the horizontal. So education on the horizontal and then age on the vertical. And you can see, like, I don't know, it doesn't quite look like there's a relationship here. But what we could do is try to predict education with age and run this model. And we see there's a coefficient here, it's pretty small, and we get a very large p-value. So we're saying it's very likely that this could be due simply to chance, that there's no relationship and we see something as large as what we do. So I would interpret this as no relationship between age and education, even though there's the potential that older people have higher education. But then we could try to predict income, log income using age. So here I have a scatter plot of age on the vertical axis and log income on the horizontal axis. What we're actually trying to do is look at this relationship. And I would say this doesn't look linear at all. But we could run a linear model on this. And we might see that there's a small effect here, that older people may be higher income by a little bit. So it might be that one of the factors impacting wages is something other than education. If I were to run this model, so I've included age. Can I hold you for just a second here? I want to show you one thing before we go. A big question we're going to try to address next time. We have a coefficient on education and a coefficient on wage. And what I want to do is compare this number to our earlier one, when we didn't include education. Sorry, when we didn't include age. So when we run just the model using education, we get a coefficient of 0.0933. When we run the model including including age, we get a slightly different estimate. So my question to you, and I'm going to show you a more extreme example of this next class. My question to you is, which one of these two numbers is right? Is this number right, or is this number right? They're very similar, but they are different. Which one of them is correct? And maybe there are other factors that may be impacting income, unrelated to age. Should we include those as well? This is actually like a sort of a deep philosophical question. We're going to pick this up next time and introduce a new idea called fixed effects. I'll see you. I have office hours right after class if you want to drop in. Take a look at the homework due on Tuesday. I'll see you all next week.